Not even that many. Here we go. Composition of functions review. Here we go. Do you guys remember doing compositions? Literally, I only have 9 slides, and one of them is the title. So, no? Okay. It's when we are plugging a function to a function. So before we start with composition, we're going to go over quickly evaluating a function, which we all should be able to do in our sleep, right? In theory, we all should be able to evaluate a function. Easy peasy, lemon squeezy. Evaluating is just a term that means you are substituting. Substitute. Pretend that says substitute. Okay. It's that I can't even accept that you. She looks terrible. Close enough. Okay. So if I'm doing this really quick, substitute, aka we're gonna plug in. Yes, no matter what it is, it just means to plug in. So our original function is this linear function here, 2x minus 3, and we're going to evaluate at these different points. So in the very beginning of your pre-algebra life, you did simple substitution. Simple substitution is where you're giving a numerical value to plug in. Do we remember doing that? So we would have 2 times 5 minus 3, correct? The 5 replaces the x, and we're left with what? What's our output? 7. Okay, that's pre-algebra. How do we feel about pre-algebra? Great. Moving on to algebra uno. In algebra uno, you're introduced to variables being able to substitute in for other variables. So in this case, I just simply have a c, and that means that c is going to take the place of x, and there's nothing else I need to do because it's not a number. I can't do anything else but substitute it in, correct? All right, then you continued and it said, okay, you can now substitute in numbers and variables at the same darn time. That's crazy, right? So now we have a number and a variable that we had to substitute in. So we have 2 times 4a minus 3. The thing here is that this was not simplified. And so this is not your final answer because when it's simplified, that means you have no unnecessary parentheses and you have combined like terms. Do I currently have unnecessary parentheses? Yes. These parentheses imply that I'm going to do what? Multiply. So I need to distribute. And that means I'm left with 8a minus 3. And then that would be my simplified form, right? Then by the end of Algebra 1, you have the idea that you can substitute in even more, not just one term, but multiple terms in for x. So this is a 2-term substitution. Terms are what we're adding and subtracting together. Make sense? So this is 2 terms, and now I'm substituting in those 2 terms. 2, 5x minus 1, minus 3. Again, this is not completed because it is not simplified. To simplify, we distribute. When there are terms, we distribute to everything, each term, right? So this was a 1 term this was 1 term, this is 2 term. So I have to distribute the 2. So we're left with 10x minus 2 minus 3. Oh, I'm done. I'm not. What did I need to do? Combine like terms. So we have 10x minus 5. Oh, now I am done. That is your pre-algebra, algebra 1 review. Questions, comments, concerns about pre-algebra and algebra 1? No. Okay, let's keep going. Okay. In algebra 2, we were introduced to composite functions. Okay. A composite function is when we are plugging a value for x, we're plugging in a whole function. Okay. Essentially, what happened right here, this is an example of a composite function. All right. It's just that we didn't define it as a function of its own. We didn't say fx minus 1 is g of x, right? So if you can do this guy, you can do a composite function. Okay. Are we, some bells are coming, some dust is being knocked off? All right. There are 2 ways that we can evaluate composite function. Okay. 2 ways. The first way is we have f. Okay, I can't write. That was an ugly f. What happened to her? Let's try that again. We have f composed of g of x. And we have g composed of f of x. When you have this little open circle, we're going to read it as composed. It is not multiply. So back in my sophomore year of high school, I call this the fog and goth process. Time to fog and goth. Okay. F composed of g of x means that I am taking g of x and plugging it into f. G composed of f of x means that I'm taking f of x and plugging it into g. It does not matter how you do it. It's just how it ends up happening. Make sense? Okay. They can also be written in terms of function notation. So the other ways that you may see it, you may see f composed of g of x, and you may see it as g composed of f of x. G and f are just names of the function, right? Those can be interchangeable depending on the problem you're talking about. All right. When working with composite function, we start on the inside. Okay. We start on the inside. Or if it's in this composite form, we start at the right, meaning I'm going to plug x into g, and then I'm going to plug that result into f. Or I'm going to plug x into f and plug those results into g. Okay. If it's in this, we start on the inside. Okay, so using this as our example. So if I'm given f composed of g of x, I'm going to first evaluate g of x. And then I'm going to use the results from g of x and plug it into f of x. Is this ringing any bells? Y'all are with me? Okay. All right, let's do it. Ready? All right, so here we're starting off with linear functions. We're keeping it simple. So we have 3x minus 5, and we have 2x plus 1. This is our f of x, this is our g of x, and we're going to evaluate them, the following expressions. So the first thing we have here is f composed of g at 3. Okay, so step 1 is you start from the inside. Starting from the inside, we're evaluating g of 3. G of 3 means I'm substituting in 3 into 2x plus 1. So we get 2 times 3 plus 1. And what do we get? G of 3 equals 7. Okay? Step 2 is to take what you got and you're going to plug it into the outer function. Our outer function is f, so now we're evaluating f of 7. So we have 3 times 7 minus 5, which gives us our final answer of 16. Got it? Guess whose turn it is for the next two problems? It is yours. So I'll be walking around. If you need me, stop me. If not, all right. So really quick on example 2B, your f of 3, right? So what did you get for f of 3? We ended up with 4. And then that we take the f of 4, I mean, 4 and plug into g. And g of 4 gives us perfect. All right. C was a little different. I'm putting the function back into itself, right? So what did you get for f of 4? And then you're going to take 7 and plug it back in, and you get 16. Oh my gosh, I'm doing this. All right. Does it change? Does the process change if I'm doing anything other than linear? No, you're still just evaluating. Okay. So regardless whether it's linear, quadratic, cubic, exponential, logarithm, doesn't matter. You're doing the same process. Okay. All right. The next part was taking equations and plugging them into each other. So actually substituting the equations in. So our f of x, what does f of x equal again? I'm sorry. 3x minus 5, and g of x equals plus 1. So here we're going to evaluate them as and create a new function. So essentially, when you're plugging a function inside of a function, we're creating a new function. We're going to call that new function h of x, okay? So what did I create from here? Well, first off, I'm taking the entire g of x and I'm plugging it in for f. So that's going to become f of 2x plus 1. Oh my gosh, doesn't this go back to algebra 1? Yes, it takes us right back to algebra 1. We went from algebra 2 now down to algebra 1. Okay? And so all I'm doing is evaluating from this point. So now we have 3 times 2x plus 1 minus 5. And I know from algebra 1 that this is not the final answer. Why is it not the final answer? It is not simplified. So we end up with 6x plus 3 minus 5, which gives us 6x minus 2. Yes, and that would be our h of x, our combined function. Yes? All right, quickly do b, just to make sure you understand it. Okay, I see most pencils are down. So for this one, we have f of x being substituted in. So we have g, and we have 3x minus 5 going in to create our new h of x. And so that gives us 2 times 3x minus 5 plus 1. Don't forget the outer parts of the function. When we distribute, we end up with 6x minus 10 plus 1. And you should end it with 6x minus 9. Yes? All right. So, as we keep going, these are additional practice problems. So we have given the following function. So now, remember I told you that those letters can be interchangeable, right? It is not going to always be F and G. We now have H, K, P, and M. Okay? So looking at H, K, P, and M, I would like for you to evaluate the following compositions. So A, you have K composed of H of 2. On B, you have H composed of M at -1. And C, you have K composed of P of X. You're going to do your best and simplify all the way down. Got it? And go. Check with your peers as you're working. Okay, so up first we have K composed of H of 2. So the first you had to do was find H of 2. And what did you get for H of 2? 1. Then you had to do K of 1. What did you get for K of 1? Did we say 10? Yes. So our final answer is 10. All right. On here, so H composed of M of -1 means I have H composed of M at -1. So my inside is M of -1. So when you did M of -1, what did you get? -1. Okay. So then we're now going to do H of -1. And when you did H of -1, you got -5. Yay. Okay. What happened? Ah, if you owe me $2 and now you owe me $3, you now owe me $5. Okay. Last was K composed of P of X, which means K with P of X inside of it. P of X equal the square root of 3x plus 1. So we have K composed of the square root of 3x plus 1. which means everywhere in K, I'm going to replace it with the square root of 3x plus 1. So we would end up with the square root of 3x plus 1 squared plus 4 times the square root of 3x plus 1 plus 5. A square times a square root sets it free. They're inverse operations. So you're left with 3x plus 1 plus 4 square root of 3x plus 1 plus 5. Last step is to combine like terms. My only like terms are positive 1 and positive 5. So our final answer would be, I'm going to write it as 3x plus 6 plus 4 square root of 3x plus 1. And there would be nothing else you can do because there are no more like terms to combine. You want to try not to put anything following a square root just because sometimes people think it's under it and it's not. Yay? Okay. All right. The next part is reading it from a table or a graph. So finding composition from a table or graph. So here we have three functions. We have a graphical version, we have a function version, and we have a word version. Okay, a written version. So the first one, our f of x here, is its own little thing. Okay, h of x is its own little piecewise. And then k of x, it describes what you have. It says I have a quadratic function with a horizontal translation of 2, followed by a vertical translation of -3. So we're going to turn k of x into an actual function. So k of x equals, I have a quadratic function with a horizontal translation of 2. So that means that I have x minus 2 squared. And a vertical translation of 3. Does that make sense? This is a quadratic function that went right and then down. All right, so now you're going to just evaluate each piece at a time. So first it says use g of 3. Where's g of 3? Where's my table? That's why I said, where's my table? Where's my table? I don't have my table, guys. Already there. All right, and g of x. So there it is. All right, so we have our g of 3. So g of 3 tells me that I'm going to be using the table first. So I'm going to go to 3 on my x. Oh no. What do you notice? There's no 3. So guess what that means? If I don't have it, how can I make it up? It doesn't exist. There is no input of 3 to give me an output. Does that make sense? All right, so here we have h composed of f of 8. So I'm going to go to f of 8 first. So going to f, this is f. I'm going to go to x of 8. When I go to 8, I'm going to follow it down to the function. And where do I stop at? -1. So my output for f of 8 is -1, which means that now I'm going to use that in h. So now I have h of -1. When I look on here for h of -1, if it's less than 1, then I use this rule, correct? So I'm going to plug -1 into here. Does that make sense? So h of -1 is the absolute value of -7 plus 3 times -1, which is 10. So my final answer would be 10. Do we see how we're using multiple representations and using different graphs, different functions? All right, now we have g composed of k of 0. So we're going to start with k of 0. So our k of 0 equals, well, we already created our k model to help it move a little faster. So that's going to give us 0 minus 2 squared minus 3. Oh, that got weird. Okay, that gives us what? 1. Because -2 squared is 4. 4 minus 3 is 1. So now we're looking for g of 1. And we get to g, and what happened? Is there g of 1? No. So then the answer is no solution. Because I can't make up something that doesn't exist there, right? And because it's a discrete data set, that means that this is all I have to go by. Got it? All right, so finish her out. Here you go. Check with each other. And we'll jump all the way to F. Okay. So F, you're starting with 3 into K. So you put 3 into K. That's 3 minus 2 is 1. 1 squared is 1. And then 1 minus 3 is -2. So now you're doing H of -2. H of -2 means that I'm using this guy, right? Because it's less than, I plug in -2. That gives me -6. -6 plus -7 gives me -13. 13 gives me, absolute value of -13 is 13. Right? And then we plug in f of 13, and what happens? Is there f of 13? No. Can I go any further? So what do I put? Make sense? Okay. Once you get to a stopping point, that's where you have to stop. Okay. All right. So your assignment should be viewable to you now. It is on AP Classroom.